Okay, here we go. I think we're recording. You guys, I think, had a pre-lecture on stoichiometry last night. So we're gonna continue with more fun stoichiometry. And yeah, that's about all I have to say right now. So we're starting with this practice problem. Theoretically, you did it, but I'm not so sure. Theoretical things aren't always reality, as we'll learn later. So we'll start with this problem. It's asking us to find the volume of hydrogen gas produced at STP when a 2 gram piece of aluminum completely reacts. So when we do these kinds of problems, always start with the given information. So we have a 2.00 gram piece of aluminum. And then, oh, that is not how you write aluminum. And then in order to get to moles, which is our most favorite unit, we are going to need the molar mass, which I see on the periodic table is 26.98. So 1 mole, 26.98 grams of aluminum. So if we look at our units, we're now in moles of aluminum, and we need to be in moles of hydrogen in order to, well, we need to switch to hydrogen, I guess. Could you guys like stop? So we know 22.4 liters per mole is our molar volume at STP, which is conveniently the conditions for this problem. So we have moles on top, so we're going to go 22.4 liters per mole. And that leaves us in hydrogen. But, or wait, did I do this wrong? No, I skipped a step. Sorry. My bad. Anyway, we're in moles of aluminum. We need to actually get to hydrogen first. Okay, to get there, very important, molar ratio. The coefficients of a chemical reaction is the molar ratio, okay? These tell you the molar ratios. For every 2 aluminum, which I'm still writing in caps for some reason, for every 2 moles of aluminum, we're gonna have 3 moles of hydrogen gas. Wonderful. Then we're now, if we look at our units, we're canceling. This is moles of aluminum here on the bottom. So now we're in moles of hydrogen. We need to cancel that out with our 22 liters per mole. If this was a problem with a solid, we would be using the molar mass here because we're going from grams and moles, but we're here with a gas. So we're left with this. And I guess I'll do this. You guys should also, well, you guys theoretically already did this, but I'll go divided by 6.98 times over 2 times 22.4, and we get 2.49. 2.49. Sorry, I need to get out of the habit of zooming in. 2.49 liters of hydrogen. Yeah? Is that what everyone else got? No? What did you get?
Got 0.00496.
Oh, yeah, because I did this wrong. It's 2 over 3. You can see the, we're doing this Kevin style with no preparation, so you can see that it's paying off.
Hey, whoa, I did my preparation.
Yeah, like 30 minutes.
Begrudgingly.
How would you get 0.0049 if you just switch it from 3 over 2 to 2?
Yeah, okay, I'm being bamboozled.
I think you just do with 22.4. Yeah.
What?
0.005. Because I did that and I made a mistake of putting 22.4.
So do we agree with 2.49?
Yeah.
Okay. I'm sorry, Jay. I guess you got vetoed. Okay, on to the new stuff.
You just decided your answers were.
Yeah, the class has decided that you're wrong, and I will trust them. So moving on. Today we're talking about theoretical yield as well as limiting versus excess reagent. Theoretical yield is, I mean, a lot of these things, scientists, or as Miss Judy has said, scientists aren't the most creative. So a lot of these things are a little self-explanatory. But as we see here, theoretical yield is the predicted amount of substance produced. produced in a reaction based on the molar ratio. Produced in a reaction based on the molar ratio. And amount of original reactant species.
Yes, my kids is absolutely incredible.
No reactant. Okay, this is not that complicated. Theoretical yield is the amount that you would theoretically get based on the starting conditions. We have this reality here because, as I mentioned earlier, what is theoretical is not always reality. And in reality, RxN, I hope you have seen before, is reaction. Reactions don't always go perfectly. They very rarely go perfectly. So we have four things that cause the reactions to not go perfectly. We can have one, a limiting reagent. Reagent is the same thing as reactant, but it's a little bit of a more lab way to say it. We can have a limiting reagent. We can have a side reaction, which is when your reactants react with something else to produce a reaction that is not the original one that was intended. We can have contamination, which is when you have like an impure substance. So whatever your substance is not actually completely what you thought. And then finally, we have reaction not working. This one is not very complicated. Sometimes the reaction just doesn't happen as much as it should. So all of these things would cause the actual amount of substance produced to be less than what the math would tell you. So in this problem above, we started with our 2 grams of aluminum and we said, okay, it's going to produce 2.49 liters of hydrogen. This is not always going to happen. So this is what we're dealing with today. So one of the things we mentioned here is the limiting reagent. And the definition of that is the chemical species that is totally consumed. Wait, that's excess. Oh, never mind. Sorry, I'm confusing myself. The chemical species that is totally consumed within a reaction. Okay.
Me too, actually. Okay.
Okay, guys.
By the way, W/N, I'm shorthand for within.
Who else to join in this?
Okay. Chemical species that is totally consumed within a reaction. Meanwhile, the excess reagent is going to be the one in excess. So the chemical species that is most likely to remain in excess after reaction. How exciting. How novel. Chemical species that is most likely to remain in excess after reaction. Trying to write a little faster, so not.
Why is it most likely and not just?
I think because things don't always go as planned, as we've discussed before. This is a kind of thing where I think it has to do with the theoretical versus actual again. Like theoretically, based on these given amount, like these initial amount of substance that we've been given, this one is going to be completely consumed, and there will be some of this one left over. But things could always go wrong, or there could be some side reaction that causes it to be completely consumed. Like things in lab don't. Oh, I mean, you guys have probably observed this. Things in lab don't always go properly, so you cannot always, especially in chemistry, say things with 100% certainty. Yes,
So is
Emin.
there a way to find out what is going to be your limiting reagent and your excess reagent?
Yes, that is what we are going to cover today. Sky, did you have a similar question?
Yeah, what are the factors that cause reaction?
These 4 things up here. that I mentioned. So limiting reagent, side reaction, I said, so some reaction on the side, contamination, like impure substance. So even if the reaction is working properly, you didn't have as much as you thought that you started with, or the reaction just literally doesn't work for whatever reason.
By the way, that says confirmation. I know it's fine, but
What?
contaminant.
Oh, sorry. I'm writing too fast.
Just because someone might be puzzled if they just.
Yeah,
saw
well,
it.
I would be puzzled by a spelling mistake as well.
I would like actually think it's spelled. I wouldn't realize it was misspelled. I'd be like, oh, okay.
I usually spell better than this. Maybe Miss Judy is under more stress than everyone realizes. Okay, steps for calculating theoretical yield based on the limiting reactant. So in typical stoichiometry fashion, we are going to have to balance the equation so that we can find our mole ratios for basically every single problem, unless they're nice enough to give you the reaction. Then we're going to do basically double calculation to figure out which reactant produces less product. So we have a practice problem here. I'm assuming that I'm supposed to work through it with you guys since we haven't done this before. So hopefully you guys are happy with that. So we have 2 silver plus diatomic iodine is reacting to form 2 silver iodide. And we're asking, if you start with 1 gram of each reactant, how many grams of silver iodide could you make? So in order to find this out, you cannot just look at the reaction and find out, oh, there's two silver for every 1 iodine. So, iodine is the limiting reactant because there's less. That's not how it works. Moles and grams and everything, you don't know until you go to moles or until you calculate the amount of product that it's actually going to produce. So we're going to do that for both reactants, assuming that we have 1 gram of each reactant. If we start with 1.00 grams of silver, we are going to convert that to moles of silver. I can see that the molar mass is 107.87. 107.87. This is on the bottom because we want to cancel out our grams. Sorry. Okay, I'll do better than that for those of you on paper. So now we're in moles of silver. We need to convert to moles of silver iodide using the molar ratio. In this case, it's pretty nice. For every 2 silver, we have 2 moles. This is also in moles. If you're confused by the ratio, you could say 2 moles. 2 moles of silver, we're producing 2 moles of silver iodide. And then you can either choose to do this step at the end, or you can choose to just leave it in moles because you can just compare between moles which one is going to be made, but it's asking us to find how many grams of silver iodide we can make. So I'm just going to do the final step and go all the way to grams. So in order to do that, we need the molar mass of silver iodide, which is going to be 126.9 plus 107.87, which gives us 234.77. 234.77 grams per mole. This is equal to if we do this whole calculation, I get 2.18 grams. Can anyone else confirm that?
234 or 107, so it'd be something here.
Okay, well, wonderful. So now we get to also do this for iodine. So we're starting with 1.00 grams of iodine. And we need the molar mass in order to get into moles. So remembering that it's diatomic iodine, we're going to do 2 times 126.9, which is going to give us 253.8 grams per mole. And now we need to use the molar ratio to convert to silver iodide. So of course we have 1 iodine 1 diatomic iodine for every 2 moles of silver iodide. And then using the same molar mass that we calculated before, because we're still converting to the same product, we have 234.77 grams per mole. And this would get us, do the math again. .85 grams, I believe. So these are our theoretical yields for each one. And we're trying to figure out how much we could make. And the limiting reactant is going to be surprise, whichever one makes the least amount. So in this case, iodine is going to produce less silver iodide than just the silver. So we're going to go with this number. Oh, wow, that is. So this is how much, 1.85 grams is how much silver iodide we can actually make given 1 gram of each reactant. Any questions on that? Okay. We shall move on then. Our next topic is somewhat similar. So in this case, we're going to be talking about impure substances and percentage purity or actual yield, which kind of sounds like what it is. So an impure substance is a chemical reactant or species that contains another unwanted substance. This is probably usually with solids. So you could have some metal contaminated with another metal or something like that. But the main idea is that if you have an impure substance, it is not entirely the substance that you think it is. So if you have, I don't know, you have a sample of cobalt, it might only be 84% cobalt. And that's the idea, is just that not the entire thing is not cobalt. So we have this way of quantifying how pure it actually is, which is percentage purity or actual yield. And we do this by the mass. So percentage purity, I'll do this in a different color. Percentage purity is going to be, this is just going to be the actual mass divided by the theoretical mass times 100%. And then our actual yield is going to be our pure mass over our sample mass times 100%. So these are both very similar because they're very similar measurements. I've noticed that a lot of the time, actually, I think they're both used pretty often. These are not usually a whole problem by themselves because they're pretty short. It's like a one-step calculation. So that, as Mr. D told me, they'll often be tacked onto a free response. They'll ask you to do this whole stoichiometry process. You'll probably have to write out the equation, balance it, do some stoichiometry, figure out the limiting or excess reactant. And then at the end, it'll say, all right, now what's the purity? So that's going to be like one part of probably like a 5+ part FRQ. So we have this practice problem here. Why don't you guys try this on your own? I'll give you like 2 minutes to try this. So for those of you watching this video, we've confirmed that what I wrote originally was actually flipped. Percentage purity, it makes more sense this way, pure mass over sample mass, whereas actual yield is what you actually got divided by what you theoretically got based on stoichiometric ratios. So our practice problem, the percentage purity of a 4.5 gram piece of calcium with only 3.8 grams of pure calcium. So this one, we're going to do percentage purity because it's giving us our pure mass over our sample mass. So we have 3.8 grams calcium over 4.5 grams, and then times 100% because we want a percentage. And this would give us 84%.
Yeah.
Okay.
It's the same thing.
So whatever calcium we were given is only 84% pure, sorry. So actual yield, this is important, very important to note. The actual yield is always less than the theoretical yield. Okay. Whatever you get is always going to be less than theoretical. It definitely can't be more. I don't know if it can technically be the same, but it should always be less. So if you get an actual yield that is more than your theoretical yield, you are wrong somehow. So we're just noting that here. Actual yield is always less than theoretical. Just back to black. Okay. So percent error, a lot of you have probably seen this formula. We've done it in, I know we did it in apes. It's a pretty common formula. It's going to be the absolute value of theoretical minus actual over theoretical times 100. So this looks like this, theoretical over theoretical. What? So we have another practice problem. This one is asking us, this is the same formula as before. We have 2 grams of silver or 2 moles of silver reacting with 1 mole of diatomic iodine to create 2 moles of silver chloride. And it says we're going to mix 1 gram of each reactant, and we actually produced 1.5 grams of silver iodide. What is the percent actual yield and percent error? So the actual yield is 1.5 grams. And what we calculated above was 1.85 grams. So our percent actual yield is going to be 1.50 grams over 1.85 grams times 100. This is from above. So our 1.85 is what we calculated up in this practice problem. We're using the same reaction and assuming the same starting conditions. So this works out to be 81%. Actually, yeah, 81% is correct, sig figs. And then it's asking us also to find the percent error. So we're going to use this formula above. We have our absolute value of our theoretical, which is 1.85 grams, minus our actual, which is 1.5 grams, over our theoretical again, 1.85 grams, times 100. And this will give us an error of 18.9%, or we can go to 2 sig figs, and we'll say 19%. So we were 19% off with our calculator. Yeah.
Didn't we calculate the actual yield? We just do 100 minus the actual yield to get the percent error. If you plug in like 100 instead of 1.85, and then the percentage 81% for 1.5, you get.
Yeah, you could probably also do that. But if you were just given, like if you're just asked to calculate one or the other, then you would use the formulas. Okay, 2 practice problems here. Miss Judy, is this practice problem is different than the one in the notebook? Okay.
But you could choose with the time. You have the time to do both.
Okay, why don't,
And probably the workbook too.
okay, why don't you guys try the first one on your own? I'll give you about 5 minutes and then we'll go over both of them together. All right, for those of you watching from home, I'm sorry about this reaction. This is probably a little bit more than you would normally get. But in case you didn't realize, I probably wouldn't have realized either. This is a gas formation reaction, which has 3 products. Normally, if you're given this type of problem, it would probably be double displacement. Yeah, that was mean. I didn't realize. I'm sorry. So the balanced chemical equation, hydrochloric acid is HCl. I'm just going to write it out balanced already. Calcium carbonate is CaCO3. And this is going to react to produce carbon dioxide, which was given to us as one of our reactants in the problem. This is how you would know it's a gas formation because we produce carbon dioxide and not just some combination of the, no. I mean, in a chemical reaction like this, I mean, all of these are neutral. None of these are charged. So otherwise, if they were charged, you would. But normally, unless we're doing like redox or some other kind of reaction, a lot of the time they're going to be neutral to start with.
Or like if the carbonate is a charged polyatomic,
Yeah.
but when it's in a bond, that charge cancels out with the calcium, so that you wouldn't
that's right.
really charge for the overall.
So we also have calcium chloride, and then we have hydrogen, or sorry, water. This is going to be also should note that the carbon dioxide is going to be gas and this water is going to be also gaseous. So now that we have our balanced chemical reaction, which is probably not what most of you were expecting, we need to, so the problem itself asks us, when excess hydrochloric acid is added to 5.73 grams of contaminated calcium carbonate, 2.49 grams of carbon dioxide is obtained. Write a balanced equation and find the percentage purity of the calcium carbonate. So in this one, they're asking us to find the percent purity of one of the reactants, and it's giving us the amount of product that is created. So in this one, we're actually going to have to work backwards. So we're going to start with our CO2, of which we have 2.49 grams. Then we're going to convert to moles. So molar mass of carbon dioxide, I do not know off the top of my head. So I would go 12.01 plus 16 times 2. To get 44.01, which sounds about right. So 1 mole of carbon dioxide is 44.01 grams. And now we need to use our molar ratio to convert back to hydrochloric acid, or sorry, to convert back to calcium carbonate, because calcium carbonate is what we're analyzing for percent purity. So according to our balanced chemical reaction, which is something you need to do correctly because otherwise you will get the problem wrong, we have, for every 1 mole of carbon dioxide, that looks like a Z. For every 1 mole of carbon dioxide, we have 1 mole of calcium carbonate. And now we need to convert to grams of calcium carbonate so that we can analyze the percent purity using our ratio of actual mass to, or theoretical mass to actual mass. So I will do the calculation. Oh, I didn't actually write the molar mass, my bad. So calcium carbonate, molar mass. Calcium is 40.08. I'm rounding these. Carbon is 12.01. And then oxygen is, we're rounding to 16. So this will give us 100.09. I hope you guys all know how to calculate molar mass, so I'm not going to write these steps down, but this gives us 100.09 grams for every mole of calcium carbonate. So if we got 2.49 grams of carbon dioxide, this tells us, according to our calculation here, if we do it out, that we got 5.66 grams that we would have started with 5.66 grams calcium carbonate. Okay, and then we need to analyze our percent purity. So again, if we scroll up, this is, I mean, it's just, doesn't really matter how you think of it, but our percent purity or our, our percent purity is going to be pure mass over sample mass times 100%. So we have our pure mass of 5.66 grams of calcium carbonate that we calculated. The problem is given to us as 5.73 grams of sample mass, which is the contaminated calcium carbonate. So we do our ratio of 5.66 grams calcium carbonate over 5.73 grams, which is what we actually got, times 100, because of course this is a percentage. And this will give us a percent purity of 98.8%. Hopefully that made more sense once you got the balanced chemical reaction, because this was a bit of a tough one to do. But this is the process. Okay. This is actually all the content for today. So we're just going to do a few more sample problems as well. But this is a very important concept because you are going to be asked to do this a lot. Is anyone still writing this down?
Can you explain again how you got the other side of the balanced equation?
Oh, okay. So one of your types of reactions that that you should have talked about at some point is called a gas formation reaction, which forms these specific products every time, as far as I'm aware. Here we have gas formation reaction right here. So let's see. When you have a carbonate plus an acid, it's going to create a gas formation reaction. So in this case, it's actually the same one with calcium carbonate and hydrochloric acid. This is not balanced here, but every time it's going to form this ionic salt with carbon dioxide gas and liquid water. So I was wrong about that. It's liquid water. But these will always be the products: carbon dioxide gas, liquid water, and then some kind of salts. So that's where you know that from. That's kind of something you would just have to memorize, as is common in this class. But generally, this would be more common with a double displacement reaction. So if we move on to this next one, we have ammonia is passed over hot calcium, calcium hydride and nitrogen gas are formed. What mass of calcium hydride is produced when 20 liters of ammonia are measured at STP and 150 grams of calcium are reacted? That's a lot of words. I would say the first thing to start with always with one of these problems is going to be the balanced chemical reaction. You also need to know your compounds so that you can do this. So ammonia is NH3. Oh, I'm still on highlighter. Ammonia is NH3. Plus we have hot calcium, which is just going to be Ca. We've not told that it's with anything else, so it's just going to be Ca. Then we are told it's calcium hydride, which is CaH2. And then our other reaction is nitrogen gas, which is Brinkelhoff, a diatomic, so we're going to have N2. And then this is not balanced. You guys should be practicing how to balance, but I already have the coefficients written down in the notes. So it's going to be 2 moles of ammonia, 3 moles of calcium, and 3 moles of calcium hydride is our balanced chemical reaction. Okay, so whenever you get a problem like this, and it's giving you the values of the two starting reactants, you're going to have to figure out which one is the limiting and excess reactant. So that is going to be our first step. Our first step 1 is going to be determine limiting reagent or reactant. Again, you'll hear reagent a lot, but it's the same thing as reactant. So in order to do this, we're going to have to, again, go through our stoichiometry for both compounds. And let's start with ammonia since it gives us that first. This ammonia is in gaseous form, as you can tell from the fact that it was given in liters. I don't think ever would see a solid measured in liters. So we'll start with our known, which is 20.0 liters of ammonia. And then we are going to convert this to moles using our standard volume at STP, since it tells us right here in the problem that it's at STP. So that is again 22.4 liters per mole. So for every 1 mole, we have 22.4 liters. Now we're measuring the amount of calcium hydride produced. So we're going to use our molar ratio, which is of course 2 moles of ammonia for every 3 moles of calcium hydride. And then we need our molar mass of calcium hydride to convert to the number of grams. Well, actually, let's see. Yeah, we'll go all the way to grams. It's a good idea. So this is not given. So calcium again, 40.08 in terms of molar mass, and then we will add that to our 2 H's. To get a molar mass of 42.1 grams per mole. And then this will give us a mass of calcium hydride equal to 'We'll go with sig figs here. So we have 3 sig figs. We'll go 56.4 grams of calcium hydride. And then we have to check the other one to see which one is actually limiting. So we didn't really get that much space here, but I'll just do it below part A. So this time we're using solid calcium. So we have 150 point grams. So be careful of this. This 150 point tells you that we're 3 sig figs still of calcium. And we're going to need the molar mass to convert to moles. So that's 40.08 again. 1 mole for every 40.08 grams of calcium. And then we're going to use our molar ratio as we do in stoichiometry. So for every 3 moles of calcium, we have 3 moles of calcium hydride. And then again, we're using the same molar mass, 42.1 grams per mole calcium hydride. And this will tell us that if we start with 150 grams of calcium, we will get 158 grams of calcium hydride from 150 point grams of calcium. So our limiting reagent is going to be our ammonia, our NH3. Question? Yes.
Why is it an excess reactant?
Sorry, our excess reactant is the ammonia. Or sorry, the calcium.
So the problem is done. I thought we're solving for the excess reactant.
Yeah, the excess reactant, to determine the excess reactant, you have to figure out which reactant would produce less product. So here we determined that 150 grams of calcium would produce 158 grams of calcium hydride, and then 20 liters of ammonia would produce 56 grams of calcium. So this tells us that ammonia is our limiting reactant or our limiting reagent because it produces less calcium hydride according to our theoretical conditions. So then it's going to ask us, this is the more complicated part, what quantity of excess reactant remains? So whenever it's asking you about excess reactant or to do something with the reactants, we're going to have to work backwards from the products. So in this case, we know that we're only going to produce 56.4 grams of calcium hydride. So go down here. We start with our 56.4 grams of calcium hydride. And then we're going to get backwards until we find out how much of our calcium remains, because our calcium is our excess reactant. So in order to do this, we need our molar mass again, which we determined was 42.1. Then we need our molar ratio, which is 3 moles of calcium hydride for every 3 moles of calcium. And then we multiply again by our molar mass of calcium, which is 40.08 grams per mole. And this will tell us that we have 53.7 sig figs grams of calcium. And this is what is used up. Okay, so assuming that we only produce 56.4 grams of calcium hydride, this means that 53.7 grams of calcium were used. So, and then in order to determine how much of the excess remains, we're going to do some subtraction, because this is the amount we used. And we started with 150 grams. So we will go to blue. Actually, we'll stay in green. So 150 grams, 150 points grams minus 53.7 grams. And this tells us 6.3 grams of calcium remains. So in general, in order to determine the amount of excess that's left over, you are going to do whatever, or sorry, I guess excess is not the best way to put it. The amount left over is going to be your excess in grams minus your limiting amount in grams. Any questions on this?
Given that you also calculated the 158 grams of CaH2, could you just take 56.4 divided by 158 and then multiply it by the quantity of the 150 in this case to get 52.7 instead? I didn't find the ratio of what is consumed. You know, the ratio. Yeah.
By doing this.
Yeah.
Who's iPhone?
Buy a mattress. Buy a mattress.
Are you a Twitter?
Yeah.
Okay, I like. Text him to the
Okay,
basketball, she's like,
we have one more workbook problem that we'll go over
well,
as well. Question 14 in the workbook, which is, spoiler alert, formatted very poorly. but will be fixed in the future for those of you, if you want to re-download it. So this one, can we stop?
What if we just were done? Like literally, team, you have no idea.
Okay, here we go. We're gonna do this problem.
No. No.
So this one is nice enough to give you the equation. You don't even have to figure it out. So 3, I don't know what this compound is called, but C2H3O2H plus aluminum hydroxide, which is AlOH3, reacts to produce 3 moles of water and aluminum acetates. So it's asking, what is the mass of aluminum acetate that can be made if this reaction is performed with 125 grams of acetic acid, so that is our first reactant, and 275 grams of aluminum hydroxide. So this is very similar to the other one. This part A is like actually up here. This is the first part of the problem, is determining the limiting reactant. So we'll start with our 125 grams of acetic acid. I guess you can write it all out if you really want. You could also just write like AC acid or something like that, so you don't have to write this all out. So we are going to need to determine our molar mass, of course, which is a little bit annoying, but we have 12.01 grams of carbon, plus there's actually 4 hydrogens here because just that's how it's written. So 4 hydrogens times 1.01 plus the mass of our oxygens, which is 2 times 16. And this gives us a molar mass of 48.05 grams per mole.
Why is there like an extra hydrogen attached from the
C2H3O2 is a polyatomic called acetate. So the H is just tacked on. Miss Judy, C2H3O2 minus is acetate, right? Yeah, so the H,
Oh, that's the poly.
yeah. So this compound right here is actually an acid. This is acetic acid. So the C2H3O2 is just a full polyatomic minus, and then the hydrogen is tacked on and makes it an acid. So we said 48.05 grams. Then we use our molar ratio, of course. So for every 3 moles of acetic acid, we have 1 mole of aluminum acetate. And then we need our molar mass of this compound, which is going to be 48.05. And we'll just add on, actually, no, that's not gonna work. So we'll just do it all again. Aluminum, 26.98 plus carbon, 12.01 times 2. Oh, wait, you have to multiply all of this times 3 because there are 3 of them. So 12.01 times 6, actually, my bad. 1.01 times 9 plus 16 times 6.
Just Google it if you want to.
And you get, what'd you get?
Did you solve it?
I got 204.13.
Yeah.
Okay. Yeah, if you're ever doing homework, you can just Google this stuff. You can Google anything, and it'll instantly give you the molar mass. I'm assuming you can add. So on a test, you will have to add, but to save yourself time, you can just look it up. So we have 204.13 grams for every mole of aluminum acetate. And this gives us, again, you can just stop at moles for comparison's sake. But if you go all the way to grams, it'll skip you the step of having to find the amount of grams later if it asks you to find out how many grams you could make given the limiting reactant. So if we do this calculation, 125, 48.05 times 1 over 3 times 204. We get 177 grams of aluminum acetate. Sorry for writing so small. Okay, now we have to do this for the other one again. So we're going to start with our aluminum hydroxide, 275 grams of it to be exact. Hydroxide is a very important polyatomic. You should definitely know this one, OH minus. And the mass of that, look that up, Charlie. Aluminum hydroxide. For every 1 mole of aluminum hydroxide, we have 78 grams. Then we go back to our molar ratio. Again, stoichiometry, this process, sometimes you'll start at a different place. It might give you moles to start with if you're lucky, but you're basically going to be doing this same process over and over again. So we're at the part where we need our molar ratio. So we have, for every 1 mole of aluminum hydroxide, we have 1 mole of aluminum acetate, which we determined was 204.13 grams per mole. And this gives us a grand total of 719 grams or 720 grams. We'll go 720 point to keep sig figs of this. I guess I'll do quotation marks. So the limiting reagent is going to be acetic acid. And then it asks, how much of the excess reagent will be left over after the reaction goes to completion? So the amount, our actual yield is 177 grams. We're going to work backwards again of aluminum acetate. And then we're going to use the molar mass 204.13. Molar ratio, which is going to be 1. We're low on time here, so I'm going to do this quickly. 1 for every 275 grams of aluminum hydroxide, or sorry, 1 mole of aluminum hydroxide. And then the molar mass of aluminum hydroxide is 78 grams per mole. So if we do this quickly, we get 67.6 grams are consumed, or 67.6 grams of aluminum hydroxide are consumed, I believe. So 275 grams. Yeah. 6. And we get something. 207 is used up. I believe this is right. You can always check me on the answer key, but that concludes our lecture for today.